First of all, thank you very much for this great presentation, in my view. One question I have regarding the position of your coil. Have you ever get any experience regarding the position of the coil in relation of the sensor and the active area of the AES calculator?
Your question is about in my cartography sensor sensitivity map. If I go very fast.
Where should I stop?
Up,
Stop.
up,
Stop.
Okay. As you see here, when my AM probe, it's spatial exploration for all the chip. Okay. Here you see that it's passed from yellow to blue, red, and black, which explains that we have four sensors triggered after I passed to 8 to 12 to 16. Why is it 16? Because it's located in the AES, and my probe is in 2 millimeter. That's explain why it's all the sensors are triggered at the same time. Okay. But if we can do a full cartography. Okay, if you want here, it's all 16 sensors because I do a coupling with the clock generator. Okay, that's why all faulted the glitch. It's in the clock generator distributed. It's like a tree if you want. We tap the first of the tree and distribute it for all the
Okay, thank you.
Welcome.
Any more questions? Okay.
Is there any chance that the noise will trigger the sensors and give you a false positive?
Yes, this sensor give me false positive. It's specifically at low and moderate clock frequency, because when the width of my detection windows is greater than the width of my injected fault in the AES. Okay, I don't know if you remind of the next last slide. This false alarm, it's the false positive.
Yeah.
Yes, I show you how we obtain. I obtain a false alarm when I reported a fault in the AES, but it's not actually a fault in the AES. Okay, I'll show you in which case and which occasion when T critical less than T over 2. Okay, after the winds of the AES, we obtain a false alarm.
And another question, I'm getting the impressions that you use multiple sensors on the AES circuit. Is that true?
Yes, it's 16.
How do you determine the number and location of those sensors?
For this 16 sensor, I can know which one of these 16 sensors is triggered or not. Okay, because it's by UR communication. I get which each sensor's behavior and state, if it's 1 or 0. Okay, I know this sensor is triggered. This one it's not.
So I'm not sure. Are you trying different locations and determine which one are effective and which are not?
I mentioned in my cartography, you see that it's a lot of color of this sensor triggered. I start from blue, which is 4 sensors, to 8, to 12, and to 16 in the middle of our sensitive area. Where the objective, it's not to study the spatial exploration of the detection sensor, but because it's already done by the designer of the sensor, the objective is to study the mechanism and efficiency of this sensor across full frequency range of the target.
Maybe there is still time for one question. Okay.
Just one curiosity, you do have false alarms. Is there a way, knowing the actual critical path of your target design, to silence them during the periods in which you now know that there are false alarms? Because from what you said, there are false alarms just because the fault takes place, but it's in a fault inert, let's call it this way,
Yes.
portion of the clock cycle.
Okay. Actually, for designer, it's for a critical path 4.5 nanosecond. It's never turned just IoT at let's say 20 megahertz because you have a big slack. Okay, and we're wasting time. That's why I mentioned here. All design and propose, for example, is 200 megahertz, the maximum clock frequency. It's around 170 megahertz, just to respect the process voltage temperature needed. That's why, okay, it's good at low frequency, but it's not good for designer in real life, how it happened in industry.
Thank you.
Thank you.
Okay, we need to go. So the time is up. We need to go to the next presentation. So if there are any questions, let's
Thank you
do
very
it
much.
offline. And thank you very much for the great presentation.